let's just make sure that we're comfortable starting this assignment. So we're comfortable with the instructions. So number 1 through 6, the instructions say write the first 5 terms of the sequence. So how do we do that? Yeah, plug in 1, then plug in 2, then plug in 3, then plug in 4, then plug in 5. Okay, let's look at the next set of instructions. It says match the sequence with the graph. Oh, the sequences are below. Okay. I was like, there's no sequences. So then below you're going to have kind of your equation. So 9 through 12, those are your equations where you're going to figure out what your outputs are. And then you're going to look at the graphs, and you can kind of match up those outputs with what the graphs would look like. So 1 through 6, so your 2, 3, 5 are going to be very similar to your 9 through 12, but it's just the graphic version once you have those outputs written down, so that's not too bad. Describe the pattern that you use to find these terms. So 13 is going to be upping the ante a little bit because we actually have to write the pattern. So when you write the pattern, your answer is going to look like 1 through 6. Okay? So if we look back in the notes, did I talk about writing patterns in the notes? Some clues for how to do that. So I talked about the typical patterns, so how to write arithmetic and geometric, right? I talked about those in the notes. Did I talk about those in the notes? Okay. And then popular patterns like perfect squares, how to do even, how to do odd, how to do alternating signs. So I gave you guys some of the beginning clues, and then from there. So to check your pattern, just plug in 1, plug in 2, plug in 3, plug in 4, and make sure it gives you those first several terms. Okay, so we have a pretty good idea of how to get started on this assignment, and then if you guys get stuck after that, let me know, and then we can do some of those together. So the majority of our time today is going to be working on this portion of the assignment, and then when we get towards the end of class, maybe when we have about 30 minutes, maybe more than 30 minutes, we have more notes to do than anything else, and then 1 through 6 will not take you very long. So after this, the other part of the assignment is Larson page 601, 1 through 6. So that portion of the assignment is kind of short, but we do have a page of notes to take before we do that portion of the assignment. So maybe when we've got about 30 minutes to go, that's when we'll pause on this part of the assignment and take the notes for the other portion of the assignment. Sound good? Okay, so I'm going to give you guys until about 9:30, and then we'll pause on this wherever we're at, and then we'll do the other portion. If you guys finish before 9:30, then we'll go ahead and we'll do the other portion of the assignment. Sound good? Okay. Go ahead and get started. Answer keys up on the back wall. 43, because number 43 is an interesting one. When you do that whole section, figuring out if they converge or diverge, you're using the limits, and you're doing the limit as n goes to infinity, so a lot of you guys have already figured out we can do n to the n FEPL. The weird part about 43 is it's sign, and it's not n to the n FEPL. I don't know, there's no s in n to the n FEPL, so a lot of students don't know what to do with the sign in 43. So I did want to talk about that because in this particular unit, sine and cosine have a unique trick to them that will be good to remember in future problems, and that shows up periodically. Okay, so for 43, when you do that problem, you're going to say the limit as n goes to infinity, and you're going to have sine n over n, and you're going to want to figure out if this problem converges or diverges, based on like writing out all the different terms. And this problem is interesting because you have to think about what happens when you plug infinity into sine. So picture plugging numbers into sine and picture the outputs of sine. So if you plug in bigger and bigger and bigger numbers into sine, does it make your outputs any bigger or smaller, or what? What happens to sine? What does sine look like as a graph? Yeah, it oscillates and it bounces back and forth between +1 and -1. So it doesn't get bigger or smaller, it just sits there and it keeps giving you the same type of outputs. Okay? So as you plug in infinity, you're not going to have anything crazy really happen to the numerator of this. It's going to oscillate between positive or -1. That, however, does not mean that you have oscillating outputs, really. I mean, you do, but not in a way that's going to infect your convergence or divergence. I mean, it's going to, but it's not going to affect your divergence. You'll see in a second. Now, what happens when you plug in infinity on the bottom? Yeah, your outcome is going to be 0. So, what if you were to look at the numbers here? Your numerator would be bouncing back and forth between like a positive and -1, basically. And then your denominator would be getting bigger, 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 which means that you would be having fractions that would be bouncing back and forth between a positive and a negative. Um, and then your fractions themselves would be getting smaller and smaller and smaller. Like your decimals would be becoming smaller and smaller and smaller decimals. So one of the tricks to this unit is then when you see the limit as n goes to infinity of a sine n or a cos n, you can almost think of that as like a -1 to the nth power, or a -1 to the n plus 1 power, because it's operating the same way. In this context, all it's doing is alternating signs. Does that make sense? So sine, in this context only, a little weird piece in this unit is that all it's doing is alternating signs. Plus or minus 1, that's all it's doing, is it's alternating signs. So it's just like having a -1 to the n in this particular problem. So it's oscillating, and then on the bottom we have an infinity, so this is actually 0. And so for 43, we would say that it converges to 0. So even though you had oscillating, but it was still converging to a number. It's getting closer and closer to 0. Does that make sense? So this is like one of those problems where it's kind of like it has a horizontal asymptote, but it's getting close to it. Does that make sense? Okay. So it's not diverges, it's actually converges, and it converges to 0. If it was sine n, it would diverge because it'd be oscillating between positive and -1. Yeah. So, and you'll see this, not all the time, but you'll see this throughout the unit, where instead of putting -1 to the n, they put sine, or they put cos. And it's just, it takes a little while to recognize, and you'll be like, oh, those tricksters, they put that in there, and I didn't even notice it at first. Okay? So, and it's specifically with the limit as n goes to infinity. So it's not that sine or cosine on their own automatically mean positive or -1. It is specifically as they go to infinity, that's when they bounce back and forth between the positive or -1. Okay, so we're going to go ahead and add some more notes. So we had our sequences. The rest of the unit is on series. That's what we are most interested in. So the rest of this period is going to be an introduction to series. And then after today's introduction, we will spend the rest of the unit getting into it. And then after this unit, next unit is also on series. So we're the next several weeks are going to be, not several weeks, but month or so. Several weeks, I don't know. However long. We're going to be working on series for a while. So here's our series intro. All right, so the definition of a series is a series is the sum of the terms of a sequence. So the way I think of it is when you write a sequence out, you have commas between the terms. When you write a series, you have plus signs between the terms. So it looks the same, you got all the terms written out, but you got plus signs in between and you add them up and you get a sum. All right? It can be infinite or it can be finite. All right, so this is the Greek symbol for summation. It's how we're gonna write sums out in shorthand. So summation, we're gonna say n equals 1, so the first term all the way to the infinity term, so going forever. So a sub n equals a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot dot dot. So instead of writing all these terms that you added up, instead of doing that, you would write the formula for the sequence, and then you would say you added the terms from 1 to infinity, or you added the terms from 1 to 5, or you added the terms from 1 to 7, or whatever, so that you have a shorthand way of writing it where you can write just this chunk here instead of writing all this stuff here. It's just a shorthand way of writing it, okay? So this literally means summation. Okay. All right, so a series converges the sum of a series goes to a specific value. That's what it means if you say that a series converges. It means that the sum of the series goes to a specific value. If you say that a series diverges, that means that the sum of a series does not go to a specific value. So there's the idea of convergence and divergence is the same idea as with a sequence. But when we were talking about sequences, we were saying the terms were getting closer and closer to a number. Now we're talking about the sums. That like as you had those terms and you were adding them together, adding them together, adding them together, it's getting closer and closer to a specific sum instead of getting closer and closer to a specific number as you wrote out the terms. Okay? All right, so let's write out the definition of a convergent or a divergent series. And this is basically what we're going to spend this whole unit studying, is what the different types of series are, what the different types of patterns are, and how to tell if they are convergent or divergent. So that's why this is an introduction, is we're just understanding what these terms mean. And then once we start getting into the rest of the unit, we'll start studying what are the different types of series, how do those patterns work, and then how do we tell. All right? So for the infinite series, the nth partial sum is So this is saying that we have an infinite series, meaning the sequence goes on forever, and you forever could be adding terms to find the sum of the series. But we have something called a partial sum, which is when you have a sum of maybe 7 terms, or you have a sum of 11 terms or something. So if they say, they might say, hold on, let me double check and see how they phrase it. I do not have it written down. Like the 5th partial sum or something like that, and that would just be the sum of the first 5 terms. Does that make sense? Okay. All right, so they say if the sequence of partial sums S sub n converges to S, then the series converges. So a sequence of partial sums is kind of a weird idea. So a sequence of partial sums says I take the first term and I write that down. That's the first partial sum. Then I take the second partial sum, which is the first term and the second term added together. I write that down next. Then I take the third partial sum, which is the first term, the second term, the third term. I write that down next. Then I take the fourth partial sum, that's the first term, the second term, the third term, the fourth term. I write that down next. Then the fifth partial sum, first, second, third, fourth, fifth. I write that down next. Then the sixth partial sum, first, second, third, fourth, fifth, sixth. I write that down next. And that would be a sequence of partial sums. Do you guys see how that could be a sequence of partial sums? I'm putting commas between all those partial sums. If I find that that is converging, that's approaching a specific number for the sum, then I can say that the overall series is going to converge. Does that make sense? Okay, it's kind of a weird idea. I'm going to say it took me a couple years for me to wrap my brain around that definition. That was kind of a weird thing. Okay, so if it seems a little abstract now, that's fine. We can come back to our notes later and read it again. All right, here's the next thing we're going to write. We're going to say the limit S is called the sum of the series. The limit S is called the sum of the series. If S sub n diverges, then the series diverges. Okay, so we're going to do 2 examples. We're going to find the sequence of partial sums and determine whether the series converges or diverges. Find the sequence of partial sums and determine where the series converges or diverges. Okay, so here's the first problem. We have the sum from 1 to infinity of n. So let's go ahead and just write out the sequence. The regular sequence, which is just what we were doing before we paused and took our notes. So what is the first term? 1. Plug in 1. What's the second term? 2. What's the third term? 3. What's the fourth term? What's the fifth term? 5. Okay. All right. So now we're going to go ahead and we're going to write what the sums are, and then we're going to write a sequence of partial sums so you guys can see what the difference is, okay? So the sum, we're going to write the sum of the first term, which is just 1. You don't have to add anything together. That's just what you get. The sequence of partial sums for the first 2 terms are going to be 1 plus 2. And what does that give you? 3. The sum of the first 3 terms is going to be 1 plus 2 plus 3, which is 6. The sum of the first 4 terms is 1 plus 2 plus 3 plus 4. Didn't need that there, which is 10. Okay. So if we write the sequence of partial sums, that would be 1, 3, 6, 10. You guys see the difference between the sequence and the sequence of partial sums? Does that make sense, the difference? Okay. So now what we would do is we would write a formula for the sequence of partial sums. That's not the easiest thing in the world to do, so I'm going to go ahead. I'm just going to give you the formula for the sequence of partial sums. So for this particular sequence of partial sums, it goes up by 2, then it goes up by 3, then it goes up by 4. Do you guys see that? It goes up by 2, goes up by 3, it goes up by 4. So the formula for this one is that S sub n equals n times n plus 1 over 2. That's the formula. N times n plus 1 over 2. So let's just double check so that we believe it. Let's plug in 1. If we plugged in 1, we would get 1 times 2 divided by 2. Does that give us the first term? Okay. If we plugged in 2, we would get 2 times 3 divided by 2. Does that give us the second term? Okay. If we plugged in 3, we would get 3 times 4 divided by 2. Does that give us the third term? Okay. And then for 4, we would plug in 4 times 5 divided by 2. Would that give us the fourth term? Okay, so we believe it. So now what we're going to do is we're going to find the limit as n goes to infinity of S sub n. What's the limit as n goes to infinity of S sub n? N times n plus 1 over 2. And it says the limit as n goes to infinity, so we can think of our n to the nFepel rules. It would just be infinity, right? Because it would be n squared on top and just a 2 on the bottom. So this would be infinity. And so what would our conclusion be? Our conclusion would be that it diverges, which I think if we look at the numbers, that kind of fits what we would expect. The numbers are just going to get bigger and bigger and bigger and bigger, and they're not approaching a specific number. They're just getting large. Okay. How do your brains feel about that example? Kind of makes sense? Okay. Let's do one more example. Okay, example 2 equals 1 to infinity, negative 1 to the n. Okay, so if we were to write out the sequence, what is the first term? Negative 1. What's the second term? What's the third term? What's the fourth term? What's the fifth term? Okay. All right. So the sum of just the first term would be negative 1. What's the sum of the first two terms? Negative 1 plus 1 is 0. What's the sum of the first three terms? Negative 1. Okay. What's the sum of the first four terms? 0. What's the sum of the first five terms? Negative 1. Okay. So if we were to write the sequence of partial sums, we would have negative 1, 0, negative 1, 0, negative 1. Okay, and so if we were to write a pattern for this, the pattern would be something like, if it was an odd term, it would be negative 1. If it was an even term, it would be 0. That's what your pattern would be. So if we did our limit, I'll go ahead and write this. So S sub n, we would say negative 1 if n equals odd, 0 if n equals even, something like that. So it'd be kind of like a piecewise function, something to that effect. Does that make sense? Are we comfortable with that? Okay, so now the limit as n goes to infinity of S sub n, and what would we say? Doesn't exist. Yeah, but it oscillates. It doesn't oscillate between like a positive 1 and negative 1, but it does oscillate between two values. Those two values are negative 1 and 0. Okay, so it oscillates, and so this diverges. Okay. It's not going to one specific number. It's going back and forth between two. Okay. All right, and so the part of the assignment that we're doing for this is page 601, 1 through 6. We're just getting a very basic understanding of how the series work. Okay? All right, brains are feeling good? Yep. Okay, perfect. Go ahead and start working on that.